I think it's fine, thank you. So yeah, I'm very happy that I have the opportunity to be here today and give this talk in person to meet all of you, and yeah, that all this worked, and yes. So my topic today will be about the so-called fiducial cell in quantum cosmology, and that is work I did together with Fabio, my former PhD colleague, and there was the paper out just I think yesterday. There will be a longer paper. I think September 21 is a little bit optimistic, but yeah, it will be out soon. So it's a little bit missing of the slides. You can also scroll through it. So the motivation for this project was, actually it's unusual that I start with formulas at the beginning of my talk. If you want to do cosmology, you usually do, if you do spatially flat cosmology, you start with this kind of metric ansatz. And now you can do two different things. You can take a full theory perspective and take your field equations, maybe the Einstein equations, you just insert this ansatz here, and then you just get your cosmological equations, and you can solve the system, and everything is fine, and there's no need for additional structures. So that would be the full theory perspective, but you could also try to construct a mini superspace model, which is important when you want to do quantization and so on. So there you would start with the Einstein-Hilbert action and insert the ansatz here. Then you will find a system which is effectively a point particle system, but your integrals will diverge because nothing in this Riemann tensor depends on the spatial point. So the integral over the spatial slice simply diverges, and what is usually done is then to introduce this fiducial cell, which is a regulator. It's a subset of the spatial slice, just in order to make this divergence regular. And the main question we had here was, how do these both pictures fit together? So here we have a field theory, we don't need divergency, we don't need fiducial structures and have no divergencies and so on. While here we have a point particle system, and we have divergent quantities and all this. So this is the aim to understand this. And further, there's the question floating around, how fiducial is this cell actually? So how does the physics depend on this? And can we really use any value and send it to infinity at the end to get rid of this regulator? So this is essentially I would mainly focus on the second question during my talk. So the plan is the following. So in the first part, I talk about the classical theory. I will give you a little bit more details about the problem and our setup. Then I will speak on the quantities which depend on these fiducial structures and how they depend on that. And then I discuss the classical dynamics. And then the second part will be about quantum cosmology, how we can represent, so how we can respect these fiducial structures in the representations of cosmology on a Hilbert space. I will discuss quantum dynamics, and what is new in a quantum theory with respect to a classical theory is that you have fluctuations, and I will discuss the effect of the fiducial cell on these fluctuations. Okay, so let's start with the classical theory. So the problem I already mentioned is the following. So you you start with a space-time, which decomposes into R times your spatial slice sigma. And then you do this metric ansatz when you do spatially flat cosmology. And you plug this into the action. It's the Einstein-Hilbert action. So it's GR coupled with a massless scalar field, which we just introduced to have non-trivial dynamics and the clock to deparameterize the system. And so you insert it into this action, and what you get is the Lagrangian, your Lagrangian and boundary terms, which we neglect here. And then you see that the Lagrangian is just this thing here, which is independent of the point. So integrating over the full spatial slice actually leads to a divergence and everything. Yeah, so this Lagrangian diverges, and so the action diverges, and that's pretty bad. So probably full homogeneity is actually too strong to impose here, because this actually leads to this divergence here. So we would like to take here a workaround around this. So we impose homogeneity only on a finite region. So we take this spatial slice sigma and we draw these boxes here. So we decompose it into subsets of sigma, and then we have these fiducial cells, the fiducial cell 1, 2, 3, and so on. You somehow count them. So you have the fiducial cell Vn. And that is a completely topological construction in the sense that it's just a matter of which subsets we choose here. However, we know that the spatial slice is actually spatially flat, and we need coordinates to define what is this box. So we define this box in terms of one of these Cartesian coordinates and say it has an edge length of L0 in any direction. So the picture is two-dimensional, but you have three directions in 3 dimensions. But this is really only the coordinate parameter, which in the given chart gives me how big is this cell. And so we have this coordinate edge length, and then the volume of that is just V0, which is L0 cubed. And I'm sorry that the notation is a little bit bad here. So with this, I mean the subset of sigma, and with this, I mean the number, which is just L0 cubed. But I think from the context, it will be clear what I mean in the following. Now you can take your full theory fields. So you have your induced metric, you have your ADM momentum, you have the scalar field and the momentum corresponding to that. And you impose that they're homogeneous only within one of these boxes. So for example, if you take the scalar field, you can decompose it as this, where this chi is the characteristic function. So it becomes 1 if x lies in the box and 0 else. And then we have here these phi n's, which is essentially then the value of the field in this box. And it can change from here to here. So we have phi 1 here, which is different than phi 2 here. And then we have another.
This is not continuous.
This is not continuous indeed.
So you will impose that conditions because of it?
We will run into problems there, yes, but we just ignore them. But yeah, so yeah, the field becomes discontinuous here. I will come to that. Okay. And yeah, you do the same thing with all the others. And here we have some remaining freedom, and we have to fix some boundary conditions for the cells. So usually what is done, so this is one of these fiducial cells I showed on the slide before. Usually what is done, you identify, you just set periodic boundary conditions, which corresponds to identifying this with torus. And yes. And then there is the freedom to, there are actually 2 remaining.
So that you identify all walls, or?
So
is it 3-dimensional?
Yes, it's 3-dimensional, yes.
So if you have a box in 2 dimensions, so the boundary is just on point.
You by identify or you impose periodic boundary conditions in each direction.
So the opposite sides.
The opposite sides, yes.
But all of them.
No pairwise. So
no pairwise.
This side is identified with this side. So yeah, so you really have a three-dimensional torus topology and no boundary left. And yeah, so you ignore everything which is outside this box basically and impose periodic boundary conditions in each direction. And this way you get also rid of this discontinuity in principle, but it's so that's just a working hypothesis, I would say. And now what you can do, and I just want to mention these two options to be clear about what we consider and what not. So you can now do a coordinate transformation. So I decide to not use my initial chart X, but I just rescale X, Y, and Z by factor beta. But then if you make everything consistent and keep in mind that this L0 is actually the size of the box in terms of these coordinates, you will find that it has to transform exactly inversely. So this is really just a matter of describing the boxes as subsets of sigma and has therefore no effect on the real decomposition of the spatial slice sigma. And so if you make everything correct and take care of all your coordinates, you should never run into problems here. So if you run into problems with that, with this, it just tells you that you made something very wrong with your coordinates and the charts you show and so on. So that is not considered. Instead, what you could do is you can really rescale the box and therefore the scale on which you impose homogeneity and also the scale on which you impose then periodic boundary conditions. So we take V0 and send it to alpha V0, which means we really enlarge this box to this bigger one here. So this box, the bigger one is really different than the smaller one because it contains more points than the smaller one. So this is really a physical change of subregions. You can imagine to do that with on the slide before, basically. You can imagine to do that with the whole grid. So you could just say, okay, I use that grid, or I make a grid a little bit larger, or factor alpha larger, and then have new boxes. And then the key question is, how does the physics change under the second kind of rescaling? And maybe there's one more thing I should say. In general relativity, we have usually diffeomorphism invariance. So saying that it actually has, so if I rescale this box by a factor of alpha, I could just do a diffeomorphism, which brings me back to the initial box again. But that is a change of my variables again. So if you consider, for example, it's written here, the physical edge length of this box. So that is like integrating the one direction along the full edge of the box. Then you find L0 times A, which is the scale factor. If you put some initial conditions and solve your equations of motion, you really can have the geometry of that slice. And if you do this rescaling, you see that the box really physically becomes larger. But of course, what you could do is you could just use another set of initial conditions, which then shrinks the box again, and then the physical size of the fiducial cell remains the same, and obviously then the physics is also unchanged. That is a thing of diffeomorphism invariance, and this is something we would like to find in the end. Yeah. So. So let me discuss now.
I have a question. So,
yes.
So from the beginning, you assume that you have a metric structure, E, because if you say volume, if you say length, you need some structure.
I agree, yes.
So you may always say that this torus is unit. That's
Yeah, if you,
and then
yes.
all this scaling, etc., means that you change the metric by conformal fact.
Yes.
So then you don't need to play the game with all these coordinate transformations. Everything can be shifted into dynamics, into the metric. So.
Yes, I agree. So yeah, this with the coordinate transformations, you don't
need coordinate.
Yeah, you don't need this.
You need
yes.
Poles, that's it.
Yeah, I agree. But in the end, it's a matter of the metric. So the conformal factor, right? Yeah. So yeah, you can put it there. Yes, I agree with that. Yes, and yeah. But the question is then still like so how large is actually then measured with respect to this metric? How large is the scale of homogeneity? So that's what we do. Does that make sense for you?
No, how large is the volume? It is included in the metric structure.
Yes.
So you integrate.
Yes.
As usual.
Yeah, I agree with that. Yes. Okay. So how does the model now depend on this? Not actually. So let's start with again a little bit of setup and which variables we choose and what we consider as observables. So the variables are motivated by a paper of Noah and Bohendorfer, and they come from the full theory again. So you could define, you can do a canonical transformation on the ADM phase space, where then one pair of observables or of phase space functions is this small v, which is just the square root of the spatial metric. And the other one is B, which is essentially, if you evaluate it, it's the trace of the extrinsic curvature, minus the trace of the extrinsic curvature. But at this point, they are completely, so we don't impose homogeneity here yet.
But do you assume that this extrinsic curvature is also homogeneous? Is proportional to the metric?
Not yet.
So there are more variables.
There are more variables, yes.
Not only the trace, but
yes. So yeah, you have 6. So you have 2 times 3, and this is just one pair of them. So and then we impose this partial homogeneity. So we say that B of x is again it's constant within one of these boxes, but it might change from box to box. And the same for this V, and here we have to take care of the fact that this is a density object. So here we introduce this fiducial metric, which is common in FPC literature, and that is just the metric like without the scale factor. So
index n is not the power.
No, it's an index, so it's not the power. So
it's the name of the cell.
Yes.
It's a dangerous message.
Yeah, I agree. I agree. Okay. So you can then from a full theory perspective, so this is what appears in the longer paper soon, you can impose this as constraints and then deduce the Dirac bracket. And what you find then is that these Bn and Vn, that they have this Dirac bracket, so that they only talk to each other when they're in the same cell, and you have this coordinate volume V naught down here. And the same, we do exactly the same construction for the matter sector, where you then get exactly the same result there. And then we can talk about observables, and we have, so these are just the metric combinations which are interesting for cosmology in the end. So all the rest would set to 0 in order to arrive at a cosmological system. And so there are also just these observables which are later interesting for the cosmological context. So you could define the volume of a certain subregion. And this is not the fiducial cell. So that is just any subregion. And as was said, it's just integrating the determinant of the metric over this volume. You then plug in this partial homogeneity and you assume that this V lies within one of these fiducial cells. You essentially just get this result. So this coordinate volume of V times the component of lowercase v in this nth fiducial cell. And so the same exists for the p phi. So also that is a density object. And these are extensive observables because if you have the volume of two volumes which are non-intersecting, then compute the volume of the union, it's just the sum of the two sub-volumes. And what you see here is on the full theory side, you have here very many different observables which depend on which set you put here. But on the symmetry reduced setting, it's essentially all of them, if you restrict to one cell, all of them are just related by a linear factor. So you could imagine that, you could, for example, take the volume of the fiducial cell and then all these observables would be just related by a linear factor. Same here. And then we can define intensive observables like B of V. So that would be the average extrinsic curvature over a certain volume. So we divide by the volume of that region, and then we integrate this extrinsic curvature over that region. And again, if you restrict, so if you insert this partial homogeneity and restrict your region to lie within one of these fiducial cells, you just get Bn as a result. And what is interesting here now is that, again, from the full theory point of view, you have very, so you have different observables because essentially I can put here any volume I like, but on the partial homogeneous setting, I have just one left. So for all volumes which lie within this fiducial cell, I always get the same result here. And it also tells us, so from that point of view, this partial, so this imposing this partial homogeneity tells us that we only have a certain subset of full theory observables available once we are once we're at the partial homogeneous setting. And what you should maybe also observe is, so what I claim to discuss in this slide is how these things depend on V naught actually, and in fact they do not depend, because so the volume of, for example, the volume of a certain region V, it's independent thereof if it's embedded in, so if I'm interested in this volume, it's independent of it if it is embedded in this cell of homogeneity or in this cell or a larger one. So it will always be the same result and the same for these things here. So the next thing is the Poisson structure. And again, so if we choose now two different subregions which both lie in the fiducial cell, and if we rescale also in the rescaled version of this fiducial cell, then as I just argued, vol V is the same in both. So it's independent thereof in which of these cells it's embedded in, so on which of these cells I impose homogeneity. And the same is true for these observables B of V. So it's independent of being embedded into this or in this. So yeah. And if you then compute the Dirac bracket with respect to the theory where you impose homogeneity on the region V naught n, then you get this result. So here appears the coordinate volume of that region. And if you do the same computation of the same observables in with respect to the Dirac bracket, where we impose homogeneity in the box alpha times V naught n, we get this result just rescaled by the factor of alpha. So from the fact that these observables are the same, we conclude that it's actually the Dirac bracket itself which has to be rescaled. So we conclude that the Poisson structure changes by factor 1 over alpha. Yes. So you have your spatial slice sigma. Now you deposit it into this grid, and you have your fiducial cell n here. And now we consider yet another volume, V, which lies in here. And then I ask, what is the volume of this region here? And it's independent of doing another decomposition where I impose, so this here would be alpha n, but one choice is this subregion V, and another choice is the choice of the fiducial cell. And now we try to understand how everything depends. So the Poisson bracket between this volume and the corresponding momentum corresponds on the fact that we have embedded it into a box of homogeneity like this, or a bigger one. So in that sense, the Poisson structure itself has to pick up this factor alpha and is sensitive to the rescaling and the choice of your fiducial or the scale on which you impose homogeneity. So the last thing of the classical theory you have to check is the Hamiltonian, and this is again a little bit tricky, or here we see exactly which kind of approximations we do. So if you take this piecewise homogeneous ansatz and plug it into the full Hamiltonian, so we start with the vector constraint, we get just 0, but the vector constraint has derivatives of the fields, and as our field is discontinuous going from one box to another, we actually get terms which are like delta distributions at the boundaries of these boxes, and just collecting them together is calling them boundary terms at the boundaries of these boxes. So you have to deal somehow with this. And if you do so plug it into the Hamiltonian constraint, you then get for each of these cells, you get this Hamiltonian, and again you get, because also there are Croce terms, derivative terms, and so on, you get boundary terms in the sense of Dirac deltas across the boundaries of these cells. And
takes the full square of the AGM momentum, not only the traits. So what we do with other components?
We just set them exactly to 0. So
you assume that the extrinsic curvature is proportional to the metric?
I'm not sure if...
Because you took a trace.
Yes.
So traceless part is 0 of extrinsic curvature?
Yes.
Okay, so this means that it is proportional to the metric.
Okay.
This is what I said from the beginning.
Okay. Sorry, I was not aware of this relation. Yeah, so then if you write down the total Hamiltonian, you have, so the vector constraint is 0. Here you get these HNs, so you have just the sum of the cells. And from now on, I ignore these boundary terms. I will discuss it again a little bit. And if you see, if you put wrong conditions on that, it will be again divergent. For example, I could say, okay, let's group together several cells and impose again homogeneity across several cells, or not take care of suitable fall-off conditions. Then I will find that this is again divergent, and so the usual solution in literature of cosmology is to restrict to only one cell. So just cut this sum off here, and by this we do two. So we do two approximations. So the first one is we neglect the boundary contributions. Boundary contributions here and here, and they essentially encode the cross-cell interactions. So they encode how does this box talk to this box, and how do they interact with each other. And another one is we restrict to one cell only. So here we certainly do another approximation where we just ignore everything which is outside the box. And this means we neglect modes which are actually larger than a single cell. Let me be a little bit more precise here. So from the full theory perspective, where we impose this partial homogeneity and that the metric is diagonal and the extrinsic approach is proportional to the metric, we have this Hamiltonian plus boundary terms. And instead, in the symmetry reduced theory, we restrict to one single n which is fixed. So we have just this, and we neglect boundary terms. And then you can compare what you actually missed by computing which modes are still contained here, and we threw away here. So you can ask which modes are still present here. So you take a Fourier transform on this fiducial background of, for example, B. What you find is that this is proportional to the product in x, y, z direction of the sign of something over this. And so this here is the edge length times the momentum in one direction divided by 2, and you have this for this contribution for each of the 3 directions. So you can plot this, and it looks essentially it looks like this. And we see that, so due to the ansatz of partial homogeneity, we essentially say we don't care about larger modes. So whatever happens inside a box, we just ignore that and we throw it away. And that's the reason why here these large momenta, they are actually heavily suppressed, because we said, so from the beginning by this ansatz, we said we're not really interested in these large modes. So they are suppressed by homogeneity. But you see that there are still modes, so here in this regime, which are actually large. So like here, they are close to 1, and they're still present. And that are the modes which have a wavelength larger than a single box. And if you look at the modes which are here, as we restricted only to one cell, you get a Dirac delta, which is just peaked at k equals 0. So we throw away all this information in this region here in the middle up to the 0 mode. And this is certainly not bad for the large modes, because they are suppressed anyhow, but it's not clear how bad this is for the small modes, because they are simply ignored. If you take the limit of the scale of homogeneity very large, and you take the limit of V naught going to infinity, you see that this sine x over x approaches the Dirac delta. So in this limit, you probably won't make too much mistakes by ignoring these modes. But as we know, if you go the evolution of the universe backwards, the universe actually becomes small, and arbitrarily small, in fact. So at the beginning, in the early stage of the universe, we have probably some picture like this. If you track everything correctly. So then we make a large truncation error, but it still needs to be examined what is the dynamic relevance of these small modes, because it might be that they are present and you ignore them, but they actually do not couple to the homogeneous sector. So we tested this, for example, for a scalar field with a certain mass, and there it's trivial essentially. There you see, you do the exact same truncation, but if your mass is large enough, these modes here, you can just neglect them. But this requires a full theory perspective, which we're not available of, at least to the best of my knowledge, to judge how bad this truncation is actually. Okay. And in order to answer the question, how does the Hamiltonian now scale with the scale of homogeneity, we see that the symmetry reduced Hamiltonian goes linearly with this volume. So if we rescale this volume, it just picks up the factor linear. So in summary, we have 3 points here where the fiducial cell enters. So the choice of this fiducial cell and the scale of homogeneity affects the available subset of full theory observables. So yeah, because they become either all the same or they are just linearly related. Second, the Poisson structure depends inversely on this. So it scales inversely with the fiducial cell. So if I enlarge the fiducial cell by a factor of 2, the Poisson structure will be rescaled by a factor of 1/2. And in turn, the Hamiltonian instead, it goes linearly with this rescaling. So if I double the volume, also the Hamiltonian becomes double. And we see here that as rescaling the fiducial cell is actually not a canonical transformation. So that means, so the Poisson structure is changed and also the Hamiltonian is changed. So V0 actually labels then a full family of symmetry reduced theories, and that they are all not related by canonical transformation. And however, there is a well-defined map between all the different V0s we can choose, because we know how to rescale the Poisson structure, we know how to rescale the Hamiltonian, we also know how the observables are related. So if we choose one V0 and someone else chooses another V0, we exactly know how we can relate these 2 theories. And this allows us now to speak about the classical dynamics. And yeah, to make the notation even worse, I drop the n index from now on in order to introduce another index, which is this V0(1) and V0(2). So with this, I mean, for example, I decide to choose a scale of homogeneity, which is V0(1), and you might choose another scale of homogeneity, which is V0(2). So this has now nothing. So now we're in a setting where we're restricted to one cell only. I'm sorry for the bad notation, but there are too many things to label. And then we define an observer which exists in a theory which with V0(1) and also in V0(2). And then we can simply compute the dynamics by taking the Poisson structure, the Poisson bracket of the one Hamiltonian in the Dirac bracket of 1. I know how to relate the Poisson bracket, so I know it picks up this factor. And I also know how I can relate the 2 Hamiltonians and picks up exactly the inverse factor. So everything cancels in the end, and in the end I find that if I compute the time derivative of this observable O, if I evaluate it in terms of the one fiducial cell symmetry reduction or the other one, it's exactly the same thing. So from that we conclude that dynamics is indeed independent of the choice of this V0. And if we're on shell, we can indeed then take the limit of V0 going to infinity. So if we're at the level of equations of motion, because the only things actually which are bad behaved is the Poisson structure, the Hamiltonian, or the action or something. These are all things you don't need if you want to do classical physics. So if you want to do classical physics, you could alternatively just start with the full theory, take the Einstein equations, restrict to these FLRW metrics, solve the system, and then construct out of this your observable O, or maybe this might be interchangeable so solving and constructing dynamics of O might be interchangeable. And you see there is no reference to the not needed, and as it is in this picture here. And the interpretation we had for this is that the classical physics is actually local, so that is not entirely true because you have to think about boundary contributions and so on. But in principle, if I have the volume here, which evolves somehow, it does not care if it's embedded in a smaller scale of homogeneity or a bigger one. It just does what it does and does not care what happens in at least too far neighboring regions. So with this, I'm done with the classical part. Maybe this is a good point to clarify maybe unclear things up to now. If there are questions. I'm sorry, I'm not done yet.
So the answer is that the dynamics is not dependent on V0.
Yes.
So we should start with V0 equal 1.
Then you're fine. Yeah. Yes. Yeah, so if you do classical physics, you can certainly do that, yes. That's the upshot, yes. Okay, then let me explain you how the situation changes for quantum cosmology. So, as I said, you have now a whole family of theories. So each choice of the knot is actually a different canonical theory. And that means if you quantize that, you have to take care of that. Each of that will need a different quantum representation. To set it up, so first of all, we do a deparameterization in terms of the phi clock. So we solve the Hamiltonian constraint with respect to this momentum p phi, which is smeared over the whole fiducial cell. And here we choose just the positive frequency solutions just for simplicity. And then we have a true Hamiltonian, which generates the dynamics with respect to this phi clock. And we would like to do a polymer quantization in V, as is usually done in cosmology, in loop quantum cosmology. And then we end up with the Hilbert space, which actually is a different one for each of the V knots, but they all look the same, so there's no explicit reference to that. And the Hilbert space is then the L2C Hilbert space, which are the almost periodic functions, so two functions over the Borg compactification of the V line. You have these states. State is now a sum over different real values, and yeah, you have this scalar product. So these basis states go with the Kronecker delta instead of the Dirac delta, and yeah, so these are just different different bases and how you express the states in terms of spaces. And now the thing is, we would like to represent the quantum operators. And if we start with the violent form of commutation relations, we find that the exponential of V operator and the exponential of B operator, they should, if I exchange them, should pick up the exponential of the Poisson bracket. And now V naught enters here. So we have to deal with that somehow. And that means we have to put it in either the representation of V or the representation of B. But what we do here is completely arbitrary where we put the V naught, but we have to put it somewhere. And this led us to the following representation. So V acting on these states mu here gives us is an eigenstate of value B nu, and we have this prefactor here which goes on with 1 over V naught to the power of gamma, and gamma plus delta appears here. Gamma plus delta is 1, and this parameterizes the freedom shifting the V0 somewhere. And this eta is just a suitable power of the Newton gravitational constant in order to get the units correct. So we see that now V picks up a factor of V0, and the exponential operator here is also a shift, which is V0 dependent. So it goes with 1 over V0 to the power of delta. And again, we need this in order to get the Poisson so the commutation relations compatible with the classical one, and get this 1 over V0 in the commutation in the end. And this tells us that if we do quantization again with the fiducial cell 1, and another one does a quantization with fiducial cell 2, we see that they can be related simply by a linear factor here. Also, the shift operators, they just related by changing the amount of shift you do. And what is interesting here is that this quantum transformation behavior is actually different from the classical one. So classically, we had that this V does not transform under changing V0, but now the quantum operator does. And that is, yes, somehow remarkable. Okay. And this allows us now to talk about quantum dynamics. So dynamics is now given by this Schrödinger equation. So the phi dynamics is generated by this true Hamiltonian, and you have then a time evolution operator in this phi. Now you have to regularize. So this is standard cosmology stuff. So you have to regularize the Hamiltonian somehow. And we follow here the standard procedure introduced by the three authors. So we just choose a suitable ordering, and the main point is to replace the appearance of B in terms of these allonomies. And then we can compute the action of this Hamiltonian on a state, and if we rewrite everything in terms of these quantities, we get this difference equation. And what is nice here is this n actually does not depend on the fiducial cell, and the only thing that depends is this theta, which can be interpreted as some effective polymerization scale, in the sense that it's the proper polymerization scale, but divided by V0. So actually we see that this equation depends also on V0, and so doing the limit of V0 going to infinity actually would make the amount of shift smaller. But it's actually not really, it's again, you cannot make it continuous by this because of the Hilbert space structure we've chosen. But the main point now is you cannot solve, or you can not try to solve this equation, but rather this one. So this is an eigenvalue equation, and the only difference is that I got rid of the theta here. So I just pull this out of the, so this just drops from the sky where I don't have any reference to theta. But once I solve this equation, I know exactly what the eigenstates of this Hamiltonian are, because I just know if this capital theta, capital phi solves this eigenvalue equation, then the state, which is this one?
Yes.
Oh, okay. So if this capital psi solves this eigenvalue problem, then I know that my psi, which is just this capital psi, so this is nu, which is the volume eigenstate, and then I just divide it by this. So this is just given by this. So I know that if this psi, capital psi E solves this eigenvalue problem, then the lowercase psi E defined by this defines the eigenvalue problem of this. And the nice thing is now that this is completely independent of V naught. And I can, from this V naught independent solution, I can construct all the solutions which are V naught dependent. Which means if I again consider two different quantizations with V naught 1 and, okay, I'm missing the, so V naught 1 and another value of V naught 2, then I can relate the eigenstates because I know the eigenstate of the Hamiltonian in the quantization 1 will just be the capital psi with this ratio, but then I can just expand and divide by theta 2, and then I know, okay, this is actually an eigenstate of the quantization in 2, but I have to rescale the volume, or I have to rescale the dependence by this ratio of the volumes. So this allows me to identify in different quantizations, I can identify the corresponding eigenstates. So I know this is an eigenstate in the one quantization with eigenvalue E, then this will be an eigenstate of the other Hamiltonian in the other quantization, but it will have the same eigenstate. If I now consistently just map one eigenstate of the Hamiltonian in the next one, I can construct this diffeomorphism, which is this isomorphism, which is just essentially the same map. So it tells me how I have to identify one state with the other. And then I will find that under this isomorphism, the decomposition in the corresponding eigenstates. So I compute the overlap between the eigenstate E in one theory and the same thing in the other theory. I see that this will be the same if I identify the states according to this isomorphism, and hence they will have the same quantum dynamics. So so the state psi 2 will have the same psi 2 evolved with the Hamiltonian in the V2 evolution, will have the same dynamics as psi 1 evolved with respect to the Hamiltonian in the one quantum theory. So it is actually possible to make again the quantum dynamics independent of V naught. So in principle, you could now say, okay, we're done. Let's just fix this V naught to be 1, and then we don't have to care about it anymore. But when we talk about a quantum theory, we're not done with that yet, because the quantum theory also contains quantum fluctuations, so it's more than just dynamics. And you can now check how expectation values change under this isomorphism. So in the following, I always mean that psi 2 is psi 1 related by this isomorphism. So these two states have the same dynamics. And if I compute then expectation values of the energy, for example, they will not change. But if I take expectation values of this V, so this is actually now really a power. So these are expectation values in higher momenta, statistical momenta. They will transform like this. And so we can just check that the volume picks up this again. Picks up this ratio to power of n, while the dimension of B does not at all transform. So you can just, that's just a straightforward computation. So the implications from that are the following. So this is actually something that is known and discussed in this paper about the mathematical structure on loop quantum cosmology. But so what you usually consider then is the observable volume of the full fiducial cell. And this is just V naught times the operator V. If you check then, how does this object transform? I just put this V naught on the other side, and then I have V naught 1 times V is equal to V naught 1 times V. So this really does not depend on V naught. So if I identify the states according to have the same dynamics, I will see that the expectation value of the volume of the fiducial cell does actually not change. But the point is, you also choose different observables here, in the sense that as it was drawn here, I not only change the region in which my observable is embedded in, but I also blow the region I consider, I blow it a little bit up. So here, two things happen at once. And however, then you can conclude that the uncertainty relation for this observable V naught, so which gives you the this observable V naught, which gives you the volume of this fiducial cell, that the uncertainty relation is just this, and this is in fact independent of the V naught quantization, because all these momenta, so all these statistical momenta do not depend on V naught. So also the standard deviation does not depend on this, and hence you have this uncertainty relation for any choice of V naught. And when you have a state that saturates this inequality, then the state mapped according to this isomorphism does also saturate this inequality. What I find also interesting to look at is the volume of so this expectation value for an eigenstate of the volume. If you evaluate this, you find that the same, so you have to do a little bit of computation, but you find that in the end, the volume you can assign to these boxes in the quantum theory is just lambda times n naught. And if you know a little bit more of quantum cosmology, you know that in the end you restrict n naught to be just an integer number, or in fact a natural number. So you see that independent of which choice of V naught you do, you can only associate the volume lambda times n naught to that region. So that is exactly what I. So if I consider this volume and ask which, sorry, and so if I consider this volume here and ask how much volume can I really, if I consider this region here and ask how much volume can I associate to that, I will get from the quantum theory this answer. If I blow this region up on a topological level, so I just take a set which is larger, so I consider this region here, the quantum theory tells me, yeah, okay, the set you consider is indeed larger, but the volume you can associate to that is still the same. And that is somehow what I discussed before. It is basically incorporates the different variants of GR in the sense that I first blow up this region, but then I'm free to do a diffeomorphism to actually map everything back again, and the theory is independent of that. Further, this tells us that to obtain homogeneity in the full slice sigma, you cannot simply take V naught and send it to infinity. You have to really pick a state for which the expectation value of that goes to infinity, because that would mean I have a box, but the size of this box is infinitely large, so it's the full spatial slice sigma. And then we can say in this limit what happens to subvolumes. So a reasonable observable is the volume V which lies in this fiducial cell. So as in this sketch here, so I consider now the volume of that here. And what I can do is I compute the expectation value of this volume in this subregion V here. And then I take the limit where, so that's just linearly related to the volume of the fiducial cell. Now I just pick now a state which exactly does this. So the expectation value of the fiducial cell goes to infinity. So I really have homogeneity on the full spatial slice. But as long as I make sure that my subset lies small enough in the fiducial cell, so I also send this ratio to 0, I can get a finite result. And in fact, I can get any finite result I want here. So for example, I could say, okay, this observer describes the volume of the universe, and I choose a state for which the size of the fiducial cell is infinitely large, but the universe is just embedded as one of the, so the observable universe is just one patch of this spatial slice, and then I get here a finite number, which is the size of the observable universe, or something like this. If you go now and compute the fluctuations for our whole universe in this limit, you find that it actually goes to 0. So in a sense, I can now control the amount of quantum fluctuations by controlling in which region, or like how large is the scale of homogeneity in which this subregion V naught is actually embedded. And yeah, this way I can make the uncertainty, so the lower bound for the uncertainty is actually arbitrarily small, and I have then, so the effective equations will be arbitrarily correct. So it's arbitrary precision. And yes, and in turn, if I was theoretically able to measure the fluctuations of the universe, so think about a very, very, very good experiment which can measure how the quantum fluctuations of some volume V are, then I can actually from this incorporate this ratio V over V naught, which then would allow me to measure what is actually the scale of homogeneity in our universe. So if I were able to measure the quantum fluctuations of the full universe, I would get this ratio here from which I can then say what this expectation value is. So in this sense, it would actually be measurable with the size of the homogeneity. Okay, so you did it. So these are my conclusions now. So from the classical theory, we learned, first of all, we have now an understanding of the truncation we actually do when we go from a full theory of gravity to the symmetry reduced cosmological mini superspace model. Further, we find that the dynamics is local and does not depend on V naught. So classically, you can really don't care about which value you choose here, as long as you're as long as you only consider on-shell expressions and are just interested in the dynamics. It's independent what you pick here, you will always come to the same result. And it is then actually possible to send this V naught to infinity. So you go back to where you started. So you consider fully homogeneous spatial slice. And that is completely possible at the classical level. In the quantum theory, the situation is more subtle. So the isomorphism, so we can define an isomorphism which relates now different Hilbert space representations. And this isomorphism is constructed such that it actually makes the dynamics independent of V naught. So also there, from quantum dynamics point of view, you say, okay, I don't care about the value of or the size of this homogeneity because the quantum dynamics is independent. However, the quantum fluctuations, they actually depend on the physical size of the fiducial cell and the scale on which you impose homogeneity. And this is basically the way it becomes physical at the quantum level. And we could still try to impose full homogeneity, which is then imposed by choosing a state for which this expectation value goes to infinity, so where the fiducial cell is infinitely large. But what we then find is that quantum fluctuations of finite volumes actually become arbitrarily small and can be suppressed to arbitrary precision. So this means, or in fact, the fact that we see that the physical size of this fiducial cell affects the quantum fluctuations makes this now a physical question of how large is the scale of homogeneity. And that is essentially the question we should deeper think about. So it may be that the universe is homogeneous everywhere, I don't know. So then we can just use a feature and see that it's very nice and these quantum fluctuations are all negligible. But yeah, it might be that it has a smaller, so that inhomogeneities are smaller, and then we have to think about what is actually the scale and how large are the quantum fluctuations. Further, we have to take into account the role of inhomogeneities, like So this is something that is discussed heavily by Boyewald in several papers. During the evolution, at some point, as I said, with the sine x over x plot, the early universe, it might be able that actually it's not valid anymore to do this truncation. So it might be too much and you throw away important information about the dynamics. You have to think about how important these are. And then if you come to the conclusion that there are actually inhomogeneities piling up, if you go back to the Big Bang, you might be in the position that you have to change the size of the knot actually dynamically. So that is something we completely ignored in this work. So for example, it might be that you have to split up the fiducial cell into subregions because it's actually better. So because it's not a good approximation anymore that your original cell is homogeneous. So you have to refine the scale. And then you end up with renormalization, and it would be nice to make contact to this line of research here. And there are also other works dealing about thinking about renormalization in cosmology. And so taking into account these inhomogeneities would automatically lead to taking into account the renormalization. It would be interesting to study how one can deal with renormalization in this context. And we thank you for your attention. Yes.
Question. So suppose that we are making the homogeneity forget that it is Earth universe, and you have unlimited technical possibilities, so you can perform any measurement which is allowed by physics, and to identify in space your elementary set. So you believe in this quantum model you discussed, or you want to believe in this quantum model, and then being able to calculate volume or even the volts in time. What would you do to find this elementary cell?
So you mean this fiducial cell, which you? Yes. So in that sense, it's really fiducial in the sense that I need to introduce it for mathematical regularity, but in the end, I would say that the universe is actually described by a state which satisfies this here, so that the volume associated to this fiducial cell is actually infinitely large, and hence I cannot. So I'm just somewhere in there, and I know that's infinitely large, but I cannot identify it because there's homogeneity everywhere, right? Does that answer your question?
So given this model and this fiducial cell and given reality, there is no way to find a candidate in the real world for this fiducial cell.
So if you assume that the universe is perfectly homogeneous, I would say no.
Because suppose that you want to check by experiment whether the model is correct.
Okay.
Correct expectation values. So in the model, you have this fiducial cell and expectation values of the volume operator. So now you would like to find even actual world. You would like to find a state.
Yes.
That according to this model is in agreement with what we find. So since the model contains this fiducial cell, you have to propose some fiducial. I'm not saying it has to be unique, but you have to. In what way could you test this model with fiducial cell, but not real unique?
So if I understand your question correct, you could.
No. If you don't understand my question correctly, then let me explain. Tell me what you don't understand, and then I will make it clear.
Okay. Let me try.
Okay. In your laptop, you have some model. Okay, some quantum model. And it consists of Hilbert space, states, operators.
Yes.
The construction of this quantum model involves something that is called space, something that is called fiducial cell.
Yes.
Okay, and this is all in your laptop. And now
I see. Yeah.
You have this world.
Yes.
And you can do any geodesic measurements.
Yes.
In what way what do you measure, and what evolution do you study in order to check the agreement of the evolution in time of the volume of your fiducial cell with something?
Yeah. So I would. So you have to measure quantum fluctuations somehow. So I can in principle define any volume, which I don't know, like.
Okay, so quantum fluctuations of what do you measure in the real world?
So, for example, if I take the solar system and I draw a box around it, I want to know how large is that. And if I believe in there's quantum gravity, I would not be able to measure this volume exact. So I could measure the expectation value of that. But if I'm able to do unlimited power experiments, I could also measure how is then the standard deviation of that. So in average, I get a certain number for the volume of the solar system, but there will be some fluctuations around it. So from quantum gravity, essentially. And if you
okay, so you take a box containing solar system, and then in what way you identify the volume of this? I guess that you measure volume of the box.
Yes.
And then you promote it to this fiducial cell in your model in order to
so it would be a sub-region.
Which is actually described actually.
So the solar system would be a sub-region of that fiducial cell, because I see that it's actually very homogeneous in the universe, but I don't know how big it is. But by measuring the quantum fluctuations of the volume of the solar system, I get indirect. So I were able to measure this thing, or the lower bound of the uncertainty relation. I could get the ratio of how much bigger is the fiducial cell with respect to the volume I consider. So if I measure that, I would know how much bigger is the scale of homogeneity with respect to the size of the solar system. And then I could tell you like what is the scale of or how big this fiducial cell is.
Okay, but is it only is it exact? So can you give some exact formula, or you have this inequality?
Yeah, I have this inequality. Yeah, so yeah, I have to think about it in more details, but in principle, all these. Yeah, let me think about it. So it is encountered in quantum fluctuations. So if you, so the problem here is that it's an inequality, right? So it's rather than an equal.
The spectrum itself, the spectrum is not.
Right, indeed, the spectrum so the spectrum of the fiducial cell would be just a polarization scale times a natural number. And then the spectrum of this quantity will be the spectrum of this times this ratio. So if you're able to measure the spectrum of the volume operator, you know is okay, you would have to know the polarizations.
Difference between one expectation value and the other. So one expectation value is in terms of okay, that one is spectrum. So in terms of space with diagonal.
Yes.
So, okay, so this is the spectrum, and lambda is some absolute value.
That's the polymerization scale. So that would be
okay.
area again.
Maybe I ask you some other questions or not? If not, let us take the speaker again. We can continue this discussion, but